Number 4.
Number 4. Right. So University College Sang-Yun-Hwang University. Where is it?
In Suwon, 40 kilometers from Seoul.
Yeah. And co-authors. Yeah, so he will speak on solitons in a chain of charge-parity-symmetric. Yeah.
Okay, thank you. Thank you very much, Slava, for the introduction. And thank you for the organizers also for including this abstract. It's a little bit different. So let's move from mathematics to physics. That's what we work. And it's a collaborative work with my colleague in the UK, Dr. Hadi Susanto, has 2 PhD students, Omar Kirikci and Rudi Kustiantara, and also another collaborative work with Boris Malomet in Israel. He has also Russian affiliation. So that's the outline as usual. We will do a mathematical model and then analytical and numerical and see what happens. So there's a trend in physics that this quantum mechanics, this parity time and then charge parity system symmetry with Hamiltonian, Hermitian, Hamiltonian. There's a lot of work in physics these days. And then what does it mean by CP? That's the charge parity. The C is the charge conjugation. That's interchange between particles and antiparticles. And then the P is the parity transformation. So that's the reverse the space coordinate. We will have applications in optics, but they have also applications in Bose-Einstein's condensates. And then we will consider the model of discrete version of charge parity invariant system. And then, again, the model is in optical waveguide. So now let's see the model. Okay, so that's the objective. We would like to construct discrete solitons, bright one, that satisfy these localization conditions. That means that for n goes to infinity, minus plus minus infinity, the soliton goes to 0. So here the model I can write down again. Actually, this is connecting with other work. So that's the model that I have over there, and then I epsilon, and then delta to un plus gamma. This is v, so that's coupled, minus I q un, and then the second equation is d dz vn equals to e I vn. This has to be square. This is vn minus I epsilon Laplacian vn plus gamma, and this is un coupled with the first one, I q vn. So here there is this term epsilon, which is called the coefficient of horizontal interside linear coupling. So if you have these dimers, n equals to 0, equals to 1, equals to 2, and so on, this is equals to minus 1, so there is a coupling between these sides. Now the other work, when epsilon equals to 0, they call it anti-continuum limit. And then of course you can just get the equation by just taking the epsilon equals to 0. So this is pretty technical. I just write it down. So this will be I u z plus u square u minus I gamma v equals to q u. And then here will be I v z plus v square v minus I gamma u equals to minus q v. So this has been done by Barashenkov, Jackson, and Flah in 2013. And there is another work also when you take this epsilon goes to infinity. So this the model becomes I u z plus u t t plus again the nonlinear term minus q u equals to the coupling term with v, and here I v z minus v t t plus the nonlinear term for V plus QV, and then the right hand side is coupling. So this has been done by also Boris Malomet with Alon Bahabat and Dana in 2015, and this one is called continuum limit. Yeah, so that's what we work is the work in between of this thing. So U and V again are complex variable, and the dots over there represent the derivative with respect to the propagation variable. In the case of optics, should be Z, so that one should be Z. And then there are a couple of coefficients I mentioned before, the epsilon positive, and then the gamma is the coupling. So this gamma is the coupling between the intercore, not intercore. They call it yes, intercore coupling between U and V. And then that delta is discrete Laplacian is like that expression. And then yesterday we heard topic about the integrable system, where I think Vladimir Sokolov talking about this KdV type of equation. So this is similar with NLS type of nonlinear Schrödinger type of equation, but they are not integrable. So the one that is integrable is the Ablowitz-Leidig type for the discrete one, and of course the NLS nonlinear Schrödinger equation itself is also integrable. And then the system is symmetric if you make transformation with the complex conjugate. Okay, so let's start with the easiest one. We would like to find a stationary solution where my solution is given by that one, an e to the power minus I kz, and the same also with b, where capital A and capital B are complex number. So now I get I don't have the term with the derivative, so that term is just the constant time A and constant times B. But I still have a linear term. And then if I substitute that term e to the power kn, then I get dispersion relation between k, capital K, and then and these other parameters. Now, maybe I have to define something here. There is what physicists call spectral band gap, because later on we will also see the stability. So that is the interval of this k square, which is the dispersion relation, interval of values of k square, which cannot be covered by the dispersion relation. Well, in this case, the dispersion relation is given by that expression with, of course, that we require this value A is less than 1 and this is positive. So now the stability condition that we have for that one is the k square has to be positive. And then for that situation we have two different cases. We have q negative and we have q positive. So for q negative is greater than gamma. For q negative is less than minus 4 epsilon plus gamma. Now the existence of solution of solitons, it depends very much on this spectral band gap. So from here again, for q positive, then again we have two interval, and for q negative we have two interval given by that one or that one and that one or that one. So it's quite technical. Okay, so that's the stability for the zero solution. Now we have the general stability. So again we take that answers an e to the power minus I kz, and then you do another perturbation, and you substitute to the to that equation, then you get a system. You have eigenvalue problem, matrix M times vector V equals to lambda times vector V. Well, this vector V is given by that one, Qn Rn Sn Tn, and we try to solve this one using perturbation. And of course, the condition for stability is the real part of lambda has to be non-positive, otherwise it will be unstable. Okay, so now let's consider two cases where they don't have coupling. So for epsilon equals to 0, so when this term is gone, and in the other cases when epsilon is small. Now for epsilon equals to 0, we take an and bn, an as real and bn as purely imaginary. And then if you substitute to equation where you originally that one without this z derivative, then you get actually that is a quartic equation in a0 square, because you take a0 outside, you get a0 to the power 8, and then so a0 being quartic polynomial. So the trivial solution is zero solution, but we are interested in non-trivial solution. And of course for quartic you can find exact expression, but we don't go into that further because it's very complicated. So again we use is a perturbation. Now again we are interested in the case where this Q is around plus minus 1, which we can scale anyway. And then we also interested in the value of intercore coupling, which is small. So we consider these two cases, and for the first case we have 4. Well, there are 3, but actually there are 4 because the last one is plus minus. So Q equals to 1 minus Q hat gamma. You get 4 different A0 and B0, and the other one also Q equals to minus 1 minus Q hat gamma. You get also 4. That's the next one. So now there are many different solutions actually. Now that's for the case when epsilon equals to 0. So now when the epsilon is small, they call it weak coupling, weakly coupled arrays. We take that ansatz and then we do again a similar perturbation. So the next term up to the second order of gamma square is given by that expression. Okay, so now let's go back to this equation. We have the eigenvalue problem, the matrix times a vector Qn, Rn, Sn, Tn with eigenvalue times the eigenvector, and then we try to solve it. But that's complicated. So again, we try to do the perturbation analysis. We substitute this into that equation for epsilon small. But then we remember that gamma is also small. So we do another double perturbation. So we make a double expansion, this x and xj, and then we substitute, and then we get the eigenvalues. And if you notice, all of them, all the eigenvalues are purely imaginary. So that indicates the stability, because remember that the condition for stability is that the real part has to be positive. Now, of course, I don't include everything there. So this is just case that one and that one. That case and that case we didn't include. At least the calculation doesn't really show maybe of the weakness of this perturbation method. But the numerical result shows that that is unstable. Okay, then let's go to numerical result. We just use Newton-Raphson, and then we do some picture here. So the left one is for the absolute value of un, and the right one is the absolute value of vn square for some parameters value. Maybe it's a bit difficult to see because the left one, there is a yellow white there, so it's a very small variation. Well, on the right hand side it's more visible. And then here is the left. There is a typo there. It should not be epsilon, but it should be n. So that's between -5 and 5. The blue one I think is u, and then the red one is v. And then the right hand side is the corresponding eigenvalue spectrum. So the horizontal axis is the real part, then the imaginary axis, vertical is the imaginary axis. And here is a function of epsilon. So initially it's just 1 point, and if you increase epsilon, then it becomes wider. And over there is at epsilon equals to 0.4. And then if you zoom in around that one, around 2, then that's actually what happened. The blue one is the approximation that we did with this expression. So you see that start to deviate. Okay, the other cases are relatively similar. We take different solution, and then a similar case also we observe that the eigenvalues change as we increase the epsilon, and then there is also, again, it's not accurate because of the perturbation method. And this is the interesting case, because before, if you notice, both two cases, all the eigenvalues are in the imaginary axis. That one also. But in this case, that case, which is case number 3 and number 4, you see that the eigenvalues, the eigenvalues there, the quartet of eigenvalues, and this case shows unstable, because there is a bifurcation. I think from here we can see imaginary of lambda with respect to epsilon. There is a bifurcation between the continuous spectrum and then the discrete spectrum over there. And then here the picture when the real part of the eigenvalues with respect to epsilon. So then you can clearly shows that the eigenvalue is, the real part of eigenvalue is positive, then it shows some stability. And then that's the picture of the soliton for unstable case. The left one is u, and the right hand is v. Okay, I think the other one is pretty stable, so it's quite similar picture. The difference is maybe the way it grows with respect to epsilon. The imaginary eigenvalue is quite different. Okay, this is also another case which is stable, and that's the plot of the imaginary eigenvalues. Okay, so I think I finish up. What we have considered is the application of this model into optic for waveguide array that emulating charge parity symmetry in the discrete system, and then we attempt both semi-analytical and also numerical, and show some family of discrete solitons. And then the majority of solitons are stable, except one that is showing instability. And then, of course, you can always extend to higher dimension, or with some other extra term, vorticity, or maybe higher order discrete solitons. Okay, so I made it in time. Thank you very much for your attention. The model. So let's go back to that model that I wrote over there. So the parity is the reverse of coordinate. I think that's the space, right? So maybe this n Yeah. And then the charge is interchange between particles and antiparticles. And then, okay, that's a good question. I have to look at it again. But if I do that transformation, this UN, if I replace, so if I have this model, if I replace my UN with Vn complex conjugate and then Vn with UN complex conjugate, you will get the same system. Yeah, but that's the charge thing. I have to look at it again. That's more a physical thing probably. But that's a good question. They have also other system which is parity time. So parity time that you reverse. I think you reverse t with minus t, and then you reverse u with also with that, and the thing is remains the same. But the charge one I'm missing in that one. Okay, so thank you. That's a good question. Okay, thank you very much.